let's see if we can't figure out what the prime factorization of 180 is. And I'm going to do this using the factor tree method. Right? You remember to do that, we just start looking for prime numbers that go into 180. Actually, any number will do, but I'm going to focus on seeing if we can find specifically prime numbers, since that's what I know we want in the end anyway. So starting at the bottom, right, does 2 go into 180? Well, yes. That's 2 times 90. Now, that 2 over there on the left side, that's a prime number, right? As soon as we get to a prime number, we stop. I'm done with that branch. I'm going to focus on the other one. So I'm going to say, okay, well, does 2 go into 90? Well, yes. It's 2 times 45. Right, so now I'm a little stuck. 2 does not go into 45. So work your way up. Right, the next prime number after 2 is 3. Does 3 go into 45? Well, yes. It's 3 times 15. And I'm going to keep trying 3 until I finally get to a no, right? Does 3 go into 15? Well, yes. It's 3 times 5. And now all of my branches are terminating in prime numbers, so I've got the prime factorization just by looking at those values. Right? Prime factorization of 180 is 2 times 2 times 3 times 3 times 5. And of course, we wouldn't write it that way, right? We're always going to simplify that using exponents. So that would be my prime factorization. Now, let me ask you a question about this. So let's try this again, but this time with a slightly different approach, right? When maybe you looked at 180, and the first thing that stood out to you was that 0 on the end, right? And if a number ends in a 0, then it's divisible by 10. Right? So 10 is going to be a factor. So maybe you looked at this and said, okay, well, I'm seeing 10 times 18. And that's fine. Perfectly reasonable way to approach this. But now you're going to have to continue working both branches because both 10 and 18, they're composite. Right? So 10, that's 5 times 2. All right, excellent. 5 and 2, those are prime numbers. We can stop with both of those branches. Focus on the 18. 18 is 2 times 9. 2 is prime, so we're done with that branch. All we have left is that 9. 9 is 3 times 3. All right, so what does that give me for the prime factorization? Well, compare that to what we got before. I've got 2 2's. I've got a 5. And I've got 2 3's. So I got the same result, right? You picked a different path to get there, but the final value was the same. The final expression was the same. That brings us to a very important result here. And this is the kind of thing that, yeah, it's a mathy thing, or sort of thing mathematicians worry about. The Fundamental Theorem of Arithmetic says that every integer greater than 1 first has a prime factorization. You can do this for essentially every positive integer except for 1. And that prime factorization is unique up to the order of the factors. Or what that part is saying is essentially don't be cute. 2 times 3 and 3 times 2 are the same thing, right? I don't care what order you list the numbers in. So this confirms what we saw on the previous slide. Right? The order in which we approach the factorization tree doesn't make a difference. Ultimately, we're guaranteed to end up with the same prime factorization no matter what set of paths we take to get there. In the next lecture, we're going to step briefly away from prime numbers and talk about what are called common factors and common multiples. Then we'll circle around and bring these two concepts together and see how we can use them to answer some practical questions.